the last domain, which is on cryptography. You can kind of see one of the things I wanted to kind of point out, just kind of as we've been working through these, just as a breakdown of the different domains of all 6. The cryptography domain, believe it or not, is the one that has the lowest percentage of, I guess, hit points, so to speak, on the exam. Not to say it's not any important at all, but it is just one of the ones that, you know, I guess maybe CompTIA thinks that this one's a little bit harder maybe for people. So maybe they lowered it that way. I don't know why they gave it such a low percentage based off of the others, but then just I wanted to point that out. And then kind of I'll jump down real quick and we'll start looking at that domain real quick. Let me change this back. Let's see. All right, so this is kind of what we'll be doing tonight, looking at cryptography and kind of going through a lot of different things here. Some of it is just knowing the terms. So especially for anybody taking the exam, if you see something that is an acronym or anything like that, make sure you focus on that, because when answering the context of the questions, you want to basically make sure you're aware of some of those acronyms. So like message digest or secure hashing algorithm, advanced encryption standard, data encryption standard. You want to know the acronym. And then also another thing to keep in mind in case I forget is that as we go through all of these various different encryption algorithms that are out there, make sure you know what camp they fit into. So if it's a symmetric algorithm, make sure you put them in this, you know that it's symmetric like DES. If it's asymmetric, make sure you know that as well and what camp it fits into.
Okay.
All right, so just kind of looking at what we've got tonight, the first thing, kind of get out of the way definition-wise, what is cryptography? The science of hiding information. And the way that we go about doing that is heavily reliant on what we'll find out in a little bit is known as ciphers or algorithms that help us to kind of transform the data from one in what we call plain text to something that is referred to as ciphertext. Now, I don't really have to make a case probably for why we need encryption. One of the things I brought up just thought was interesting, of course, as everybody probably knows already that's watching this, the Apple debate that's going on right now with the FBI, and the importance of that and the precedents that it's actually setting. For that point alone, we probably know why cryptography is pretty important. So it is used heavily in systems today to protect the data. All right, so basically where we'll start this off is just kind of talking about encryption and decryption and what that process looks like. So basically, encryption takes something that is plain text and it converts it to what is known as ciphertext. And so an example of something like this, let me see here, let's go to here. You can come in here and this particular site, and I'll kind of share it just in the links here. And on this particular site, what you can do is you can use this site to go through and look at what it is to transform data from one version of text, from plain text to what is known as ciphertext. And it's relatively easy. In fact, one of the classic things, if you've got something like Linux, I was going to copy this real quick. If you wanted to see a very simple tool that is used for crypto, is to use something like this. So what this does is it does what is known as ROT13 and transferring the text so that it goes 13 positions. It's known as what we call a shift cipher. Okay, so you could try out something like this and you can actually transform the data into something that is from plain text to transfer it over to something like ciphertext. So that's kind of neat to see how the actual encryption process actually works. Now, there is also a key component that makes encryption possible, and it's the use of what is referred to as a cipher. So the cipher is the steps, if you like, or the series of steps that the plain text will go through to actually transform the data from plain text to ciphertext. So that's an important aspect, and a lot of times just the simple thing is just knowing that a cipher is what is actually the responsible party for transforming that data is a really important point to make. Now, there are several different types of ciphers, and we'll talk about some of those, but usually they fit into one camp or another. So it's either usually a stream cipher or a block cipher. So stream ciphers, basically they use this process called XORing to XOR the data, and it does it a bit at a time. So that's the key thing to make sure you're assured with and understand with something like stream ciphers. A good example of a stream cipher is RC4. The Rivet cipher is one of those algorithms that's there, or excuse me, ciphers that's there that does encryption 1 bit at a time as a stream cipher. Block cipher, another type of the other type, takes a 64-bit block of data at a time and takes that block of data at a time and does the encryption here. Problem with doing it this way, even though it's going to be stronger, more secure because it has the ability to use better mathematics or better processing, it's going to be slower at the overall performance side. So if a stream cipher is fast, because it has to be fast to encrypt 1 bit of data at a time, block cipher is going to be a little bit slower, but can be used with stronger encryption. So a lot of what we would see today, like AES, we're going to use something like a block cipher in that case. So you've got those two types of ciphers. Now, the next point to make about using cryptography, or what are some of the goals of cryptography? So if we look at Security Plus, we've already mentioned the main goal of security is to provide confidentiality of services or data integrity and availability. And so with cryptography, it focuses, at least at first, outright, heavily on confidentiality. How do we protect the data that's in transit? How do we protect the data in use? How do we protect the data that's at rest? All through the use of some type of crypto. Okay. It also can do integrity. So you have the ability to do things like digital signatures and the ability to do checksum values on encryption to validate that it's not been tampered with or been modified. And it also provides non-remediation. So if you look at digital signatures, the only way in this case, the way that crypto works is with a digital signature, I take a message, I hash it, I encrypt that hash with my private key, send it to its destination, and then you decrypt it with my public key, and the only person that should have access to your private key is that particular person. So I right there prove that it actually came from that person unless somebody has access to their private key, of course. So it does provide a lot of different things, and of course, as we look at systems that we want to provide encryption of a whole, like BitLocker or using Veracrypt or something like that, that actually does full disk encryption, the overall goal is to protect that data at rest so that someone, as an intruder, they can't brute force the actual system to try to gain access to the system. So that's kind of, again, the same lines as the Apple thing. They're trying to, kind of brute force it to allowing them access to the system. A lot of good open source tools out there that are used for crypto. And so one of the ones that, I think right away is, OpenSSL. So if you look at OpenSSL, oh, sorry, can you pause it?
Yeah.
It's not a big deal. I'm sorry, buddy. Hang on 1 second, okay?
All right.
I'll be right back, Corey. Come here.
It's hurting, all right. It's hurting.
Okay, it's just a cuticle, Bob. Come here. Did you kill it or something?
No, I just.
Play with it?
Yes.
Come here. Hold that on. Hold that on. Sorry about that.
Oh, not a problem.
Sometimes you have emergencies. All right, hold on a second. Let me get, I was going to put some stuff here. Let's see. I think that's right. Nah, let me add one more in here just in case.
I would probably say out of all the security, like true quote unquote security, cryptography, just, I don't know. I guess I'm so interested in it because I don't understand it.
There's so much of it, dude. There is just so much of it out there.
I mean, I guess I understand the basics. I mean, you know, different standards use a different algorithm to encrypt things in different ways, and they're either harder or easier to break. But
let's see. I'm going to put these in here too. And let's see. I'll just do all this now. That way we got it all in there. Let's see. And that's all I need. I'll put some more in here. That way I can just kind of get all that out of the way.
well, you did a lot of legwork getting this session set up.
Well, there's just a lot of, you know, this is a lot of stuff I do kind of in the classes, you know, kind of demo. I figure I'd just throw them in here. All right, that should be enough. I think I'm ready now. Okay. You tell me when you're ready.
I'm good to go.
All right, so kind of looking at the switching gears here a little bit for a second. The next thing we kind of need to talk about is a particular type of ciphering that we can do, a particular process known as steganography. So steganography is probably one of those worrisome processes that you kind of worry about because a lot of times it's used for nefarious purposes to you know, hide secret data inside of something ordinary. And so let's say if in this case I was a disgruntled employee for a company and I wanted to be able to hide some of their trade secrets or some stuff I had access to that was company confidential documents, so I could, you know, export those out and maybe sell them off to the highest bidder. So what steganography is just that, having the ability to hide information. Again, that information can be large sets of information to small sets of information, it doesn't matter, but hide it in ordinary stuff. So you can hide it in graphic, you know, pictures and stuff like that. There's a great tool. Let me see if I can find it real quick for you. That basically does that. I don't have an example to show you, but it's a real nice tool that you could use. It's relatively lightweight that helps you to kind of hide stuff. It's called image hide. And what it allows you the ability to do is take a picture, and then from that picture, go ahead and stuff in it. You know, maybe it is a particular plan, or maybe it is if it's a, you know, I guess a drug dealer, and maybe it's we're going to meet at midnight, you know, or something like that. So it can hide anything inside of the image, and then not only can it hide it inside the image, but it can also be encrypted as a part of the image. So really kind of could be used for really deceitful stuff. Now, it doesn't have to be all bad, because you could use steganography if you're a privacy advocate as trying to be able to make sure the information, you know, spy kind of information maybe, doesn't get leaked out to someone, right? They don't know what to look for unless both parties are the only ones that are privy to the communications of the data. So anyway, we can hide stuff in movies if it's very large data. We can hide stuff in sound files. Cool thing about sound files is the way it hides stuff is it hides it at levels of audacity that you can't hear as a human. So it's that kind of neat stuff. Or in movies, it hides it in certain frames of the movie, so where you can't see the information if you're not really looking for it.
Gotcha.
So a classic example of this be something like spam mimic. That's another thing that I put in the links there. You basically come in here and you say, I want to encode something. And then maybe it is a short message. You know, 6:30, and you want to have in a message, you can go and encode it and outputs it to what looks like spam. And then nothing in here tells me any of that stuff. But the other person, if I copy that and send it to them, they come to this site and they know that we're using that as a form of communication. They could then decrypt the message and then get whatever that was the information there. So steganography, really cool at being able to hide information. Now, can it be used for bad stuff? Absolutely. So you can absolutely use this as a technique to hide things like malware. So, I mean, again, malware can bind to anything. And so it is just one of those causes for concerns that basically not only could it be used to exfiltrate trade secrets out of a company, but it could also be used for even more nefarious purposes, and the use of something like malware, hiding it with malware.
Gotcha.
All right. So the next thing we'll talk about here, kind of look at what is a one-time pad. So one-time pads, basically what they are, is kind of like Google Authenticator is a good example. And what it's doing is it's going to rotate, the time-based one at least, is going to rotate the value every 60 seconds so that it's a unique value every 60 seconds tied to the device in most cases that it's installed on. And it's an ultra way to, or a way to create an ultra unique characteristic for things like encryption authentication. And you can kind of think of it like this. If we were able to pinpoint a particular time, particular day, particular noise, right? We're able to create that level of entropy when we do encryption, that unless there's absolutely a way to capture that on the other end, unless you know that particular frequency or whatever it is, then that makes like the highest level of crypto that you can have if you can use something like that. Okay. So one-time pads are great ways. You can use them with dual, multi-factor authentication. You can also use it as a way to encrypt data. So hashing, another thing here to kind of focus on a little bit with crypto, a one-way encryption process, right? So the biggest thing really to know about hashing is that you don't use it to go in the opposite direction like you do with a lot of encryption. Like if you take something like, we talked about earlier, using something like a shift cipher or Caesar cipher or ROT13. Well, I know with ROT13, I'm shifting 13 positions. So I know if I go minus 13, then I'm going to be able to decrypt the contents.
Mm-hmm.
With a hash, you're more interested in creating a unique value for the data so that you have a one-to-one relationship with whatever the message is, the input is creating a unique, what is referred to as a digest. And then you can send or store that digest, and then anytime the information needs to pass across networks, it can use the digest as opposed to the plain text nature of the message. When it gets to its destination, then it uses that particular hash to be able to compare in the password database, for example. If the password is entered correctly, then it will hash the password and it will match the hash that's stored in the backend database. Okay. Now the problem with hashing though is you've got things like CrackStation. So basically, CrackStation, if I can get your hash, okay, what it does is it allows me the ability to go in and input it into this particular place. And what it will use, things like rainbow tables, right, to be able to try to crack the password. And so you can see here, it supports a wide variety of different hashes. So if you put them in here, then you can use something else to try to crack the password, because what it's going to do, what password cracker works, is it's just evaluating what the hash is against a known hash so that we can have that one-to-one relationship. And then once it's discovered, then there's no way to spoof a hash. A hash value in this case should be whatever is the same all the time. Okay, so it does very much help us to have hashes because it provides a form of digital integrity.
Okay.
So we use it for passwords. We use it for a lot of things, believe it or not. The hashing algorithms that you need to know for the Security Plus are going to be message digest, and there are several versions of that. There's MD5, MD2, MD4, and or there is also secure hashing algorithms. So that's another one of the ones, or SHA, that you're going to want to know. Now, are there others? Yes, there's Tiger, there's RipeMD. There are several other examples of hash algorithms out there, but those are the primary ones you want to know for the test. MD5 is a 128-bit message digest. That's how large of a digest it produces. However, MD5 is no longer considered useful for hashing because of a thing called collisions. And what collisions are with hashing in the hashing world is that it's not able to create a one-to-one relationship. So if it's no longer able to create a one-to-one relationship, and there's chances that I have two different inputs that are producing the same output, then it's not serving a hash's purpose anymore. So that's why it's kind of been deprecated and is no longer considered of use anymore. So everything now has moved to the secure hashing algorithm. You can kind of see that there's several different veritable links of the digest that can be created with the secure hashing algorithm. Downside-wise is performance, right? In this case, as we grow those sizes of the digest, to be able to create those, it's going to cost from a performance perspective, and that's it. It might not be noticeable, but that is going to be what the cost is.
So, and a hash is mostly used for verification. So you would, well, I guess you would encrypt something and then generate a hash for it, and then if you downloaded that same encrypted file or what have you, and you ran, let's say, SHA on it, you should get the same hash as the hash that someone else has gotten.
Right. So, like, let's say, there's a couple different scenarios you can use it for. So let's say I want to send you a document. So I take that document, I hash it. It creates it creates a hash. Then I encrypt that hash with my private key. Now, when I send it to you, as long as you have access to my public key, you can decrypt the hash. Now, what you do is you take that document and you hash it, and if it has the same value as the one that I sent you, then you know it hasn't been modified. Does that make sense? Because the hash is the same that you calculated as the one that I sent you that was encrypted.
Okay, gotcha.
Hashing is also used with Windows, and in Windows for password management or authentication, we use what is known as the NT landman hash. Now, version 2 is what we use today. Older versions of Windows use NT landman version 1. The problem with NT landman is it doesn't do anything for key stretching. So the value of the key is what it is. It doesn't do anything additionally like salting the hash to create a higher level of entropy. Okay. So again, there's some other ones there that you could use as well that are, also the same thing, hashing algorithms. All right, so then we kind of switch gears a little bit and talk about symmetric encryption versus asymmetric encryption. So in the notes there, I sent you kind of some examples on how to hash and how to use symmetric and asymmetric encryption using OpenSSL. So you can use that. Another really good tool, I forgot to mention this, if you want to do like hashing and kind of play around with it a little bit, is a tool called HashCalc. So it's a good enough of a learning tool that you could use there to go off and get an idea of what hashing is all about. Okay. So anyway, symmetric encryption, the thing I want to know about it is it uses one key for both encryption and decryption. Now the problem with that is, well, we got to protect that key, right? Because if somebody was to get that key, then they would be able to decrypt anything that was being communicated. So the problem with symmetric encryption is key exchange. Okay, so we don't have really a great way to handle key exchange. We have to do everything in what is referred to as out of band to be able to exchange keys with using symmetric encryption. So I might be in an email conversation with you, but then I physically have to put the key on a USB drive and physically hand it to you as a safe key exchange because it's out of the current band of communication that we're doing through the use of email. But the advantage to using symmetric encryption is it's super duper fast. So again, there's always going to be, with security in general and or just technology in general, there's always going to be pros and cons. Okay. For the test takers, you do want to know that there are several names for symmetric encryption. So we can call it symmetric encryption, but we also can call it private key encryption. We can also call it secret key encryption or shared key encryption. So those are just different names. Just like with hashing, you can call a hash a checksum. You can call a hash value. You can call a hash a digest. Okay. So also for the test takers, and really this is just something you almost have to kind of create like a flashcard almost concept. You want to be able to, like I said in the beginning, put an encryption algorithm under a particular umbrella of what encryption is provided there. So these are the symmetric encryption algorithms that you want to know. DES, triple DES, AES, Blowfish, Twofish, and Rivet cipher. Okay, so out of the list here, most of these are block ciphers. The only stream cipher in the list here is RC4, right? And we talked about stream ciphers before. Most of the block ciphers will do, at least the default is, 64-bit blocks. However, you can see with AES provides the option to choose 128, 192, and several different bit block sizes as well. So do know that as another thing, I guess. And so focus on here, what is the bit length of the key sizes and what is the block size that is being used, because that has a lot to do with how well it performs and what level of entropy is provided. So like blocks, even though DES is a block cipher, it only does a 56-bit key. So there's a very low key deviation or a very low key work factor there because of the size of the key, okay, itself. All right, so that's symmetric encryption. Now, asymmetric encryption, on this realm, we really have to use two keys. In fact, this is called two-key encryption with asymmetric. We use a public key and a private key for doing encryption. Now, the advantage is here with the private key, I can keep it private. So no one should have access to the private key. This is an advantage because then the public key can be equally shared out for anybody that wants to encrypt the information and send it along to me from a communication perspective. So you encrypt with the public key, and then when it reaches its destination, that person that receives that incoming message can decrypt the message with their private key. So there is a separation of keys. They're providing a level of a better level of key exchange. However, con-wise, asymmetric isn't as fast, right? So there is pros and cons to all of the encryption and everything we've talked about so far.
If somebody had your public key, could they not reverse engineer the encryption?
No, they're 100% unique to each other. So the AES, or the private and public key, are exact opposites of each other.
Okay.
So here, asymmetric encryption, again, under that umbrella, we want to be able to put these different encryption algorithms that we need to know. So Rivet's cipher, or excuse me, RCA, Rivet's was one of them, is the most popular one that we see today. So if you go off to a website that's HTTPS and you go and view the details of that certificate, there's a good chance that you'll see RSA being used for public key crypto today. Diffie-Hellman is still used today, but Diffie-Hellman is almost exclusively used for key exchange. So key exchange, an important aspect we already talked about, is how do I safely get you the key that you're going to need to pass encrypted messages along to me. And then ECC has started to take over some of the low-end computing devices and or even smartphones. So when we do like cellular encryption, we're more than likely using ECC as the one there, because it doesn't require as much performance for calculation, computational, that something like RSA does. So RSA requires more resources to be able to do the encryption versus something like elliptical curve cryptography. All right. So again, there's key exchange. Kind of mentioned what that was used for. We got to make sure that the keys get to the point that the user can use them, but needs to get there safely. So typically, the best of both worlds would be use something like a symmetric key cipher to do fast encryption, because it can encrypt really fast, and then use something like asymmetric encryption to do something like key exchange. So that's a lot of what you get today when you're using something like public key infrastructure, is you're using, in this case, that mixing of the two.
Gotcha.
All right, so we also need to know what digital signatures are, and the idea of digital signatures. I kind of already mentioned that, but really what digital signatures provide us by being able to produce something like this is a form of non-repudiation, so that the receiver can verify that they received it from the original source. And then in addition to that, it provides, because we are doing hashing, it provides a level of integrity. Okay, so not only does it do integrity checking, but it also provides non-repudiation. So it's very useful as well. Now we can do digital signatures a variety of different ways. In fact, one typical maybe example of something like this might be using a service like Hushmail. So if you can find somebody, or even if you want to do it with yourself, you can actually use Hushmail to do PGP end-to-end encryption over your email messages. So you could sign up for an account today, send maybe your Gmail account an encrypted email, and then you could encrypt it, right? So if anybody was to ever intercept that message, they wouldn't be able to read it. It would just look like a bunch of garbage to them, because it would be using cryptography to be able to do that. So not only can you use it in that fashion where we're encrypting, but it can also be used, I can extract your digital signature from a message and then validate that it actually comes from you. So that's kind of neat as well, by using the sender's public key to extract that hash value. All right, let's see what else we need to go over here. Talked about inbound, out of bound, block, stream. All right, so let's talk key escrow for a second here. So if I'm using public key, private key in my environment, what a key escrow allows us to do is set aside encryption keys, so that if somebody, let's say, was under investigation, if it's the company, or the company itself was about to sell off its assets, and it wanted to have the ability for a third party to interact with those assets in the environment, maybe it's because they are under investigation, or because that maybe, like I said, selling off the company. What a key escrow allows us the ability to do is set aside cryptographic keys that could allow access to the information within the environment. So key escrow, very useful for those types of things. Just as well, another one that you might hear from time to time, I don't see it listed here. Oh, here it is. You might see a recovery agent be one of the things that, in this case, would be useful in that scenario. So a recovery agent basically is, I've got several admins that they need to be able to, if the person is not available, maybe they're on vacation, or the person leaves the company, they need to be able to access their encrypted documents. And so what you can do is you can set up a data recovery agent. And basically what it does, we use group policy to push out the public key that everybody is going to use to encrypt the folder that they're going to encrypt, basically use in Windows using EFS encryption. And then anytime that scenario happens, when an admin needs to come in there and access a user's resources, they can access those resources. So it's creating an environment where not only is the user going to be able to protect the data by them doing the encryption, but it's also going to govern them by making them also encrypt that data by using an administrator's recovery agent key.
Gotcha.
All right, let's see. Talked about key escrow. So just really quick, as a side note, I don't see this mentioned here that I can tell in this section. Oh, here it is, perfect forward secrecy. So what perfect forward secrecy offers us, and one of the links I gave you guys to check out was SSL Labs. Go to SSL Labs, challenge you, and go and look at some of maybe your credit card sites you visit or your bank sites and some of those, and let it test those sites. And one of the things that it will test for is perfect forward secrecy. So what perfect forward secrecy, to put it in a nutshell, does is the ability for a session key to be derived long-term. It is not an option if perfect forward secrecy is enabled. So as you would expect, what do we use a session key for? They kind of mentioned a session key here. It's the ability to encrypt the message, okay? So if we are going through and encrypting the message, what would happen if perfect forward secrecy was not a feature that was enabled? Then what I would do as a bad guy is I would capture lots of the conversations that are encrypted right now, and then I would try to brute force the session key. Now, like you probably already know, eventually brute forcing is going to work, okay? Don't know how long, maybe it's 5-10 years, it's going to work, okay? Once it works, now because all of your content has been encrypted with that session key, not only can I access the things you now encrypt with that session key, but I can also access anything that you previously encrypted with that session key. So you can see that that's not a good thing in all scenarios, and why you would want perfect forward secrecy. Because with perfect forward secrecy, if I capture your communications and I break the session key, I can only access the content that was encrypted with that session key and that session key alone. Does that make sense?
Yep.
So that's another thing that is an important aspect to protecting the data assets in the environment, is perfect forward secrecy. All right. Let's see. Let's go back here. Keep me on track. So key stretching is another thing that can be used in cryptography as a technique to provide a higher work factor overall for cryptographic processing. And so what this does, and you probably say, well, gosh, I really don't want to add a requirement for using more resources to be able to do the encryption. Well, maybe in some cases you do. And there are a variety of different reasons, obviously brute forcing being the biggest, most glaringly obvious one, to why you would want to make that encryption key stretch, right? And to make it stronger and harder to crack, right? Now, one classic implementation of key stretching is the use of salts, okay? So if you don't know what a salt is, I put in the notes there a OpenSSL way to go off and use salt. Salt is adding randomness to the actual encryption process. Randomness that has nothing to do with the overall input that's being put into the encryption process. So the next thing then becomes, well, what happens if I don't know what the salt is? You just don't decrypt the data, right? So you must, if you're going to use something like this to add a higher level of entropy or work factor to the encryption process, to the outputted ciphertext, enhance it, you must absolutely know what to take away so that you can get what is the intended outcome if you're going through the decryption process.
So going back to the idea of ROT 13, if you just shift each, so you have a message, you shift each character 13 13 places. With salting, you would basically just at a predetermined interval, say every fourth entry, you add a random character in there.
Right.
Okay.
Right. Or another way to look at it is, let's say we're going to use encryption, and it's a straight up math process, right? We're doing something exponentially. And what we do a little bit different this time around, as opposed to doing it just one time as the cryptographic process, we do it 16 times. So you literally take the input and you go through an encryption mathematical process 16 times to produce the output. So now you've got, not only do you have the crypto that was used, the algorithm, but you also have a variable that is used then to increase the level of crypto that's being used, because you're doing the encryption so many more times to get it further and further away from what the original was.
Okay, and somebody would have to know that you basically re-encrypted that 16 times to get there.
Yeah, but if they did, then they would be able to absolutely decrypt the contents.
Yeah.
All right, so key stretching is an important aspect, and some of the approaches to key stretching are going to be important for us. So password-based key deviation, function 2 is a part of the public key cryptography standards that they mentioned as a part of RSA. So that's one of the examples. And of course, using a salt is a part of that. And then bcrypt is another example, using blowfish cipher. So there are examples of it in the wild that allow us to add those iterative rotations or loops of encryption, in addition to adding things like salt that add more entropy that has nothing to do with the input that is being actually put into the encryption process.
Gotcha.
All right, so I don't know. I guess that is all that I see here. So let me just go back to some of the things that might be missing. So the last part here, I guess, before we kind of wrap up, is it talks about looking at public key infrastructure, right? So public key infrastructure, yes, it is absolutely a part of our PKI infrastructure, certificate services or cryptography, but it's a whole bunch of things. It's not just we're using a symmetric key or we're using an asymmetric key. It's a whole bunch of things. In fact, for the test takers, you want to know what each one of these is. So first one is a certificate authority. The certificate authority in this case is the centralized authority that is going to issue a public key private key pair for use in authentication, encryption, integrity, digital signatures, all of those types of things that we kind of just mentioned. It is the end-all be-all when it comes to a trusted relationship with a person that issues digital certificates.
And that's basically, so like GoDaddy offers SSL certs.
That's it.
They're just a third party that basically goes, yeah, I vouch for this person. They purchased a cert through us. Yeah.
Right, and that's important to know, because there are public CAs and then there's private CAs. So public CA would be like, like you said there, GoDaddy. Okay. But somebody like, if I'm wanting to be able to have all my users digitally or digitally sign Word documents, I might not want to expense out all of those certificates I have to create through a third-party CA. So I can use an internal trusted CA for something like that.
Gotcha. Okay.
Now, the next one we need to know is, from time to time, certificates, like a lot of things, go through a life cycle. So the life cycle of certificates starts with issuance. And really, that's a part of what this is. This is a certificate signing request, which is a process that the certificate entity, the user, has to go through to actually get a certificate and be able to start using a certificate for data encryption. But eventually, let's say if a certificate becomes compromised, then the way that we want to make sure that that public certificate is no longer used for anything out in the real world is we want to revoke that certificate. And the way that we can check to make sure the certificate is not been revoked, or how do we keep up to date, or whatever it is through the use of what are known as certificate revocation lists. They're the entities that we can look to if we want to evaluate to see if the resource has been compromised. Now, the problem with the certificate revocation list is that it can get really large. And so if the client is going to go off and parse that entire certificate revocation list, that might be performance intensive on the client machine and or cause a stalemate, so to speak, in some accessing of content that is using certificate services. So this guy is a service that can do the work for the client and check on the status of the certificate. It's known as the Online Certificate Status Protocol. It will be an alternative to a certificate revocation list and the typical client actually going off and parsing the information, as opposed to having a service that can dedicate towards it. All right, so those are the components, and there's one more that's missing in there. It's kind of mentioned here. It's referred to as the registration authority. So the registration authority is going to collect the information that is going to be needed to pass that information along to the certificate authority, so that it can determine whether or not it wants to issue a certificate to whatever is the end user, computer, or whatever. So that plays a vital role too, and the process of creating certificates is the registration part.
Gotcha.
And then I guess that's pretty much it. The only other thing that I can think of with public key infrastructure that you want to make sure that you are aware of is the trust models that are out there. Typical trust model that we use with certificate authorities today is the use of what is known as a hierarchical model. And it has at the very top what is known as the root CA. And the root CA, its only purpose and design in this type of topology or this trust model is so that it can issue certificates to subordinate CAs or the lower level CAs. And then once it's done that, it gets turned off, because you don't want to have that root CA get compromised and not be able to start from scratch with that root CA. So usually after that root CA has issued certificates to the subordinate CAs, you cut it off. And then the subordinate CA actually is the one person or a computer that's going to be the person that you're going to contact as a user if you want to request certificates for issuance for use in cryptography, data encryption, or excuse me, digital signatures, and those types of things.
Gotcha.
So that's one more thing they might show you there is what are the different trust models of creating a public key infrastructure service today on networks. All right. So I really don't think there's anything else I had there that I can tell in that. Any questions on anything, Corey? I think that's it, Bo.
I don't think I have any. No, I think I'm good.
Okay. Well, just I guess make those links available if you can. That way, some people, if they wanted to kind of play around with some of the crypto stuff, they can kind of play around with it or whatever. And I guess if you guys get together on some kind of test prep, let me know or something.
Will do. Yeah.
And
they
then
will probably do that sometime this week.
I'm definitely gonna make the next week's meeting, so I guess we'll have a lot to talk about then.
Yeah, definitely.